Welcome to this explainer. You know that feeling when you look at a crazy quantitative reasoning problem and your brain just screams, "Start crunching numbers!" Or maybe you just want to run for the hills. We've all been there. But today, we're doing things differently. We're going to unpack a complete lesson on conquering these exact problems by leaning on pure mathematical logic, completely skipping those endless, messy calculations. We are building a structural toolkit that's literally going to change how you see numbers.
So, to kick things off, is it actually possible to outsmart a math test? Well, yes, absolutely. Because the secret sauce isn't calculating harder or faster. It's about deploying strategic structural logic. Today, we're exploring 3 specific tools that act like massive shortcuts through the mathematical weeds. They'll save you a ton of time and, more importantly, guarantee you get the right answer.
Here is our agenda. We're building this toolkit step by step. First up, absolute value fences. Then, the seesaw of averages. Next, we hit the data laboratory. And finally, we'll talk about the limits of induction. Let's get right into it.
Starting with Part 1, absolute value fences and how we use them to trap the right answer.
Okay, let's dive right in. Our very first tool is all about absolute value inequalities. Now, I want you to think of these as building literal mathematical fences on a number line to instantly trap your answer. To solve one of these, you always split it down the middle into 2 paths. Step 1 is super straightforward. You just set the positive boundary exactly as it's written. So, x plus 2 is less than 4. Easy, right? But step 2 is where you've really got to pay attention. When you introduce a negative from that second boundary, you absolutely must flip the inequality sign. Why? Well, think about it. 3 is definitely greater than 2, but negative 3 is not greater than negative 2. So to keep the universe mathematically intact, the sign flips, making x plus 2 greater than negative 4. Now, these quantitative problems absolutely love to turn up the heat by giving you simultaneous inequalities. When that happens, you just systematically find both sets of boundaries. Let's say for set A, our algebra builds a fence trapping all the numbers between positive 2 and negative 6. But then set B builds a totally different fence, trapping numbers between positive 4 and negative 3. All of a sudden, you're staring at all these overlapping constraints, and honestly, it looks incredibly messy if you're just trying to plug numbers in blindly.
But here's the trick. This is exactly where we apply what's known as necessary and sufficient reasoning. We actually don't need all 4 of those numbers to build our final master fence. We just need to find the true overlap. Look at it this way. If a number has to be greater than negative 6, but also greater than negative 3, well, anything greater than negative 3 is already greater than negative 6, right? And on the flip side, if a number must be less than 4, but also strictly less than 2, being less than 2 is the tighter rule. So just like that, we've successfully narrowed our true mathematical fences down to exactly negative 3 on the bottom end and positive 2 on the top.
Now that we've got our fences up, we can just take a stroll through our cleanly fenced yard. If the question asks for the integers trapped strictly between our final boundaries of negative 3 and positive 2, we just list them out. Remember, we don't include the boundary numbers themselves, so we're looking at negative 2, negative 1, 0, and 1.
Count them up, and we've got exactly 4 valid integer answers. No way around it. That brilliantly illustrates how finding the structural fences completely solves the problem for us. Notice what we didn't do. We didn't do any massive complex arithmetic. We just logically deduced the boundaries, mapped where they overlapped, and counted what was left inside. That is the true power of tool number 1.
All right, moving right along to part 2, the seesaw of averages, balancing to 0.
So, if you ever run into a problem that mentions an average sum of 0, I want you to immediately picture a perfectly balanced seesaw in your head. The rule for this is absolute. Your negative values on the left side of that seesaw must perfectly cancel out the positive values on the right side. In a completely symmetrical example, negative 3, negative 2, and negative 1 precisely balance out positive 1, positive 2, and positive 3. The sum is exactly 0.
But remember, this seesaw is totally unyielding. It acts like a strict equation. If you take that positive 3 and suddenly shrink it down to 2.5, you've just taken physical weight off the positive side. To stop the whole thing from crashing down, you have to adjust the opposite side proportionally. You'd have to push the negative 3 up to a negative 2.5. The key takeaway here? No matter how you shift these values around, the positive weight and negative weight must perfectly counterweight each other.
By visualizing the problem like this, you instantly see the logical constraints of the numbers and you completely avoid testing dozens of terrible fractions.
Let's jump into part 3, the data laboratory, where we stress test our scenarios.
Our third tool takes this whole logical framework and applies it to data comparison problems, treating them like a literal laboratory experiment. When a question asks about real numbers without giving you any restrictions, you absolutely must plug in extremes. For instance, in scenario 1, you might plug in some standard everyday integers like 1 and 2, and maybe quantity B wins. But our logic toolkit says we cannot stop there. We have to stress test it. So, for scenario 2, you test tiny decimals, like 0.1 and 0.01, and suddenly quantity A is greater.
This is absolutely crucial because it shows us exactly why standard mathematical dominance isn't always a permanent thing. As numbers get incredibly small and start inching towards zero, a seemingly tiny multiplier can suddenly become mathematically dominant. It honestly feels like a betrayal of our basic intuition, but it's a fantastic reminder that the number 1 behaves very, very differently than 0.01.
Now, this whole testing methodology serves a very specific strategic purpose. If your different scenarios lead to the greater quantity flipping back and forth, sometimes A is bigger, the next time B is bigger, you haven't failed. You've actually successfully proven that the answer is definitively D, which stands for cannot be determined from the information given. Finding D isn't giving up. Getting to D is the answer. By trying 3 distinct scenarios, say positive integers, negatives, and tiny decimals, you save yourself immense amounts of time on an exam. You prove the inconsistency, mark D, and you confidently move right on.
And that brings us to our final section, part 4, the limits of induction and why logic has to be your ultimate tool.
As our source material astutely points out, just mindlessly testing numbers leaves you highly vulnerable to a concept philosophers call the problem of induction. Now, what does that mean for us? The problem of induction is the very real risk that you just simply haven't tried the specific numbers needed to break the pattern yet. You may test 3 normal integers, see the exact same result every time, and assume it's a universal rule. But you completely forgot to test a fraction or a decimal or a negative number. That is exactly why, as you try different numbers, you have to continually overlay it with solid logic. So, here's the ultimate question. Will you let blind calculations limit you, or will you use logic to absolutely guarantee your answer? Today, in this explainer, we've built a comprehensive system. We learned how to establish absolute mathematical boundaries, we visualized the strict zero-sum seesaw of averages, and we stress-tested data in our own little laboratory. You've transcended just doing math to actually analyzing the architecture of the problem itself. Thank you so much for joining me today. But before you go, ask yourself this. If pure logic can bypass complex arithmetic on a math test, what other invisible, complex systems in your everyday life are you overcomplicating right now?